Good afternoon and welcome you all to the seventh talk of Bangalore India Nano Monthly Webinar Series 22-23. The Vision Group on Nanotechnology, Government of Karnataka, under the Honorary Chairmanship of Bharat Ratna Professor C.N. Rao, who is the Honorary President of JNCSR, and also the Chairmanship of Professor Navakant Bhatt, who is the Dean Division of Interdisciplinary Sciences, Indian Institute of Science, has initiated this webinar series. This is the seventh nano talk in this series actually. And today's guest speaker is Professor Mandar M. Deshmukh, Professor, Tata Institute of Fundamental Research, Mumbai. And topic of the proposed talk is quantum noise limited amplifier using graphene. I welcome you, sir. Now I request Professor Anindya Das, Professor, Department of Physics, Indian Institute of Science, and convener of Bangalore India Nano Monthly Webinar Series, to introduce the honorable speaker to the participants. Thank you, sir. Please.
Yeah, thank you, Venkatesh, and good afternoon to everyone. It's my great pleasure to introduce our today's speaker, Professor Mandar Deshmukh. Professor Deshmukh doesn't need any formal introduction. He's a renowned and eminent physicist and well-known both nationally as well as internationally in the field of nanoscience and nanotechnology. He has been role model for younger generation for doing, mesoscopic physics in India. For example, myself motivated for during my PhD time to even till today, motivated by many of his experiments, and it still motivate our generation for doing nanoscience and nanotechnology. I'll briefly mention his biodata. Professor Mandar Deshmukh is currently professor at Tata Institute of Fundamental Research in the Department of Condensed Matter Physics and Material Science. Before joining TIFR, he did his postdoc from Harvard University and PhD from Cornell University. He obtained his undergraduate degree from IIT Bombay. Just to name, he is recipient of several prestigious awards. To just name few of them, he is recipient of Swarna Jayanti Fellowship from Department of Science and Technology. He is recipient of Santi Swarup Bhatnagar Award, B.M. Birla Science Prize Award, IBM Faculty Award, and many more. So I will not waste any more time. So today he is going to talk about quantum noise limited amplifier using graphene. Mandar, stage is yours. Yeah.
Okay, thank you very much, Dr. Venkatesha and India, for the kind invitation to this forum and for the kind introduction. I'm really happy to be here. So let me start with my talk. Let's see why. Okay. Okay. All right. So Anindya had mentioned to me that there is a lot of interest from students who are interested in applications of devices, and that's why I chose this one particular part of our recent work, which is to look at an amplifier made using graphene. This is a special kind of amplifier called the quantum noise limited amplifier, and I'll tell you about it. I want to briefly acknowledge the funding agencies that make this research possible, which is Department of Atomic Energy that funds our research at TIFR, and Department of Science and Technology of India that really make this work possible. So at the outset, let me make sure that I sort of point out the people who actually do the hard work. This is a photo from a trek that we took with my group. These are the students who work with me who actually do really the exciting work, and I'm fortunate to be working with them. Joydeep is the person who led this particular work on amplifiers, and there are a lot of collaborators, including my colleague R. Vijay at TIFR, and we have some collaborators who supply really important material for making some of these devices. So let me tell you a little bit about what we do at TFR. We look at lots of different aspects of nanoscience. We look at flow of electrons in a number of different kind of devices, which is called quantum transport. We look at mechanics of small devices, which is a field called NEMS or MEMS. We look at magnetization or magnetic materials. Then we have also a significant effort looking at superconductors, high temperature superconductors. And in the last several years, we have been focusing on graphene Josephson junction, which is going to be at the center of today's talk, which is how one can make. I'll tell you what Josephson junction is and how this works as an amplifier. I'll try to keep things simple. So in order for me to proceed, let me give you a brief outline. So I'm going to tell you about what 2D materials are. Many of you probably already know well, but let me tell you a little bit. Then I'll tell you about graphene. Then I'll go a little bit more into detail of what this amplifier is, which is to essentially amplify very small electrical signals coming from quantum devices. And then I'll briefly mention, if there's time, how one can make scalable architecture and what more can be done. So, something like, 17 years ago, which is around 2005, there was a lot of excitement because a number of different groups, including the group of Andrei Geim and Kostya Novoselov, they accomplished something, and a little bit later, Philip Kim at Columbia University, they figured out a remarkable thing, which is to take a piece of graphite and to peel off one layer of that graphite, and that material is called graphene. So this isolation was very surprising, and people thought that this was not possible. So these researchers accomplished this, and that has opened up a very big field. These materials are truly two-dimensional because it's only one atom thick, and it is like a sheet. Following that, or rather copying that protocol, a lot of different two-dimensional materials have been discovered, starting from insulators, semiconductors, superconductors, and a lot of the technology is also being driven by some of these 2D semiconductors, and a lot of industries like Samsung have invested heavily in developing next generation devices. So it's not clear where it will go, but there is a significant effort. So this big idea of two-dimensional materials has opened up a new field. And one of the exciting aspects about this field is sort of like a Lego toy. One can peel off one atom thick layers of different materials and put them on top of each other. And you might say, why should one do something crazy like that? And the reason for that is simply to accomplish devices which weren't possible earlier, because growing these kind of layer by layer, very different materials was not possible. There are techniques like MBE, but they cannot grow the kind of diversity of materials that you can achieve by putting one on top of each other. So this has opened up a kind of a vast avenue for research and also for technological application. So graphene is this sort of sheet of hexagonal sheet of material where you have carbon atoms at each of these sites, green and orange. The green and orange sites are somewhat different, but it's a little bit technical. So right now, let's forget about it. These sites A and B are very different, but they're occupied by the same carbon atom. And the fact that they are different makes a huge impact on the electrical properties of this one sheet of graphene. So I'm going to skip a little bit of this, but whenever physicists or material scientists try to understand any materials properties, electronic properties, they try to understand what is called the band structure. So what is a band structure is basically energy and momentum relation. So if we have a ball and I throw a ball, I know that the energy and momentum have a relationship, which is E is proportional to velocity square or momentum squared. Now, when electrons are moving around in solids, they don't have that relation. It's actually can be quite complex. And so this is the energy momentum relation in sort of the momentum space. And this is needed to understand any material's electronic properties. So if one does that, one finds that the material graphene is actually a semi-metal where this sort of fabric, kind of touches the lower part. And this semi-metal part is going to be kind of important. What is intriguing about it is that at these special points where the two kind of manifolds touch each other, the energy, which is the y-axis, and the momentum are linearly related, which doesn't happen in solid state physics. I'll explain with contrast where it happens in physics in our world, sort of our experience. And that makes this material interesting. The fact that energy is proportional to momentum doesn't happen for most electronic materials. And that is sort of the exciting part of this system. So this is the relation, and often to understand electronic properties, so this energy is very high. So often physicists and material scientists will say, oh, our electrons will not access this energy. So we will only look at what is the relationship in this narrow range of energy and write down the behavior of the electrons. And it turns out this behavior of electrons, this is sort of a mathematical way of writing it, is very unusual and gives the electrons in graphene unusual properties, which have a way of allowing the electrons to travel longer before they change their momentum. So now you might say, what's the Nobel Prize winning worthy aspect of graphene? So the world around us that we see every day, and the electrons in most other materials, the energy and momentum I already mentioned is related quadratically. Okay, so these are strange. These are particular kind of particles called Schrodinger fermions, and the world of particles which are moving at velocities close to the velocity of light or at velocity, relativistic particles, their energy momentum relationship is linear. Okay, these are where do you find these particles? So for example, there are particles called neutrinos, or also particles in accelerators in CERN or elsewhere, where they are relativistic and energy and momentum is linearly related. But what is unusual is that in graphene, which is electrons moving in graphene, behave like the electrons that are moving at velocities close to light. Okay, they're not moving at velocity of light, but nevertheless, their description is the same as that of these particles which are moving close to velocity of light, and that makes it very exciting because you cannot realize some of these experiments in this particle physics. You can realize in experiments with graphene, and that's why this system is interesting. So as I already told you, there are lots of different materials. Graphene, there is a cousin of graphene, which is called boron nitride, which I will talk about. They are similar in the sense that graphene has carbon atoms everywhere in this mesh, sort of like a jali. And boron nitride is also, boron and nitrogen in the periodic table are on either side of carbon. So if you take together boron and nitrogen, they are same number of electrons as two carbon atoms. But the property of this boron nitride is very different from the property of graphene. Whereas graphene is a conductor, boron nitride is an insulator. So just by changing a pairs of atoms, which actually have the same number of electrons taken together as a pair, you can tune the properties. And this is a little bit technical, but this simple choice of elements changes the properties profoundly. So there are, okay, let me see. I hope this works. So how does one make graphene? I'm an experimentalist. I understand the theoretical part, but I want to make it. This is the method by which the Nobel Prize winning experiments were done. This video is available from a YouTube video. So you take a piece of graphite, put it in. So what's amazing about this field is that it uses a method or for research, which is sort of what would be the intuition of a child who is asked to make something small by peeling it off. But simple ideas can lead to very exciting scientific discoveries, and one has to sometimes try unusual and creative things, and that's what the Nobel Prize winning researchers did to make this one atom thick graphene for their experiment. So this is not a scalable process that you might not make a integrated circuit with this, but it actually showed the possibility that you can make this device. So once you have this kind of graphene, which is very thin and then thicker pieces, so many layers of graphene makes it thicker, and very thick ones make it shiny mirror-like. We want my lab wants to make electrical measurements, so we want to make electrical connections. So for that, we follow a process which is known as nanofabrication or lithography, and that uses some polymers, some plastics, which are sensitive to beam of electrons to pattern electrodes. So if you know Rangoli, then this is the same spirit as Rangoli, which is to make a stencil, but this stencil is made out of plastic. So you make some holes in the polymer, and then like sprinkling of the powder of Rangoli, you put it and you sprinkle atoms of metal like gold, and they will go and sit on the graphene through these holes. And that allows you to make electrical connections to graphene where you want. So it does not rely on random chance. This is the graphene that I wanted to contact, and I made these holes right over it and sprinkled gold, and I have the contacts. And then the beauty of this process is that I can remove the plastic and the metal on top, and then only thing that is left is these gold electrodes, and I have what I want to accomplish, which is electrodes put on graphene. And this is sort of crudely what an old device looks like. And now, just to give you an idea, this is 80 micrometers. So human hair diameter is about 80 micrometers. So this is one human hair, and this is the device. Of course, this is very old kind of device, but just gives you an idea. It's 1 atom thick, but roughly 1/3 the diameter of a human hair is monolayer graphene. So I told you that graphene has this peculiar property that it is a semi-metal, not a metal, not a semiconductor, but or an insulator, but somewhere in between. And that's because of this property that two bands touch each other at a point. And when I measure the electrical resistance of this device in a geometry of a transistor, so what I do is I take a sheet of graphene, I connect it with 2 gold electrodes, and I measure the resistance of this circuit. And I have a third electrode, which is a gate electrode, which is underneath the insulator. The green thing is an insulator, which doesn't conduct. So when I apply a voltage, I can actually put more electrons in graphene and the resistance reduces, or I can put more absence of electrons, which are called in physics are called holes. So the resistance as a function of gate, which is a kind of a transistor, looks something like this. So the unusual and somewhat frustrating property of graphene is that it cannot be made incorporated in the transistors that we use in everyday life, because it's a tap which is leaky. So when you use electronics, you want a tap, which is a basic unit of an electrical circuit, is a transistor which turns off so that the electrons or the tap of electrons doesn't flow, or you want it to flow fully. The disadvantage of graphene is monolayer graphene is that the tap actually never closes. It either flows faster or less, but never turns off. That's one of the reasons why monolayer graphene is not used for integrated circuits that we have around us. But there are other materials like semiconductors which actually do exactly what we want, which is to turn the tap of electrons on and off. So I gave you a brief introduction of 2D materials and graphene, and I'm going to tell you about this particular amplifier that we make. Something might be technical, but I try to simplify and give you the essence as we go along. So many of you might have heard of qubits, which are basically the basic units of quantum computing, and a world around. There are lots of experiments going around. In fact, now many of corporations like Google, IBM, and many others have a significant effort in making integrated processors with many more qubits. Okay, so they have 2 states, and you can think of a qubit as basically a loop of current where one state corresponds to current flowing in one direction, and 0 state corresponds to current flowing in the other direction in a superconducting loop. And that basic way can lead to some unusual and exciting things like a superposition, where the current is a superposition of electron flowing in one sort of a clockwise direction and a current flowing in the anti-clockwise direction. So nevertheless, to measure these qubits, you have to measure the electrical signal that comes out of the qubit, and that electrical signal is very, very small. This is 10 to the power 16 minus 16 watts, which is 0.16 zeros and a 1. Typical bulb that we might use, let's say LED, will be like 5 watts or something. So this is very small power. This power cannot be very easily measured. So you actually need an amplifier immediately to measure a qubit or any kind of quantum device. So the amplifier is kind of denoted by this triangle. So an amplifier has 2 properties: a gain, which is how much it increases, and the noise temperature. So let's take a step back and ask what is amplification. So if you have used a kind of a speaker from your music system or your Bluetooth speaker from your phone, connected to your phone. When you increase the volume, that is sort of like the gain. But what you sometimes may not realize is that anytime you have a gain, the amplifier adds some something other than the original electrical signal, but noise, and that's in old kind of speakers, it's be like something not a pleasing sound. But you cannot get amplification without noise. That's basic thermodynamics of basic law of physics. So you need an amplifier to measure qubits, and not just one, but in fact you need many a chain of amplifiers. So you have an amplifier, first amplifier, then another amplifier, and so on. So that sounds easy, but the problem is that the noise that all these amplifiers add can actually become quite substantial. So if your original signal is very small and you keep on adding more and more noise, then if you don't think carefully, then you will completely wash away the original electrical signal. So it's important to consider particularly what is the amplifier's contribution, which is characterized in terms of a temperature. So larger the temperature, larger is the noise. You can think about it. The first amplifier's noise temperature or contribution of noise gets there as is. The next stage noise is added, but it's reduced by the gain of the first stage, and so on. But the overall system's noise can never be less than the noise of these, because these are all kind of small but positive numbers. So it's very important to choose the first amplifier which adds the least amount of noise. Okay, and that's where this noise amplifier, the quantum noise unlimited amplifier that I'm going to tell you briefly about, is very important. It adds the least amount of noise that is allowed by laws of physics. Okay, and it's used in all kind of amplification of electrical signals coming from all kinds of quantum circuits. So it's already been used. It's very common. It's called Josephson parametric amplifier. I'll tell you a little bit about why this name is there. But it's an amplifier, and it adds the least amount of noise. It allows you to see lots of interesting science and also technology. Okay, you can measure qubits and other devices so this is charged qubits much more easily than you would do if you didn't have an amplifier. So it plays a very critical role. So now you would say, if there are already amplifiers like this, then why should one make another kind of amplifier using graphene? Why, kind of reinvent the wheel? So there are reasons to make a new kind of amplifier with graphene, this parametric amplifier, because there are certain experiments where you want to operate it in high magnetic fields. You want a tunability of its center frequency with an electrostatic gate, and you can also make sensors using this architecture. So this is the reasons which motivated our work. So what is parametric resonance? So I will skip the equations, but I'll show you the picture. So if you, I'm sure, you were, at some point when you were a kid, you were using a swing. And for the swing, what happens is that you stand up and go down at different points of your, as the swing is going back and forth. And as you move up and down through this, you on your own, without anybody pushing externally, you are able to make the swing go back and forth. That process is understood in mechanics. It's called parametric amplification. Okay, when you change this up and down, you're essentially changing the description of what is called the pendulum, and that allows you to amplify mechanical motion. So that parametric process is well known, and what you have experienced in your everyday life is sort of written in terms of this mathematical equations, but these are equations which describe the motion of a pendulum, if you like, or a mass attached to a spring. And what they're saying is basically, if you follow this process of changing, essentially the mass attached, its position relative to the length of the pendulum, you can reduce the losses, which is any damping that you have will get reduced, and that is basically amplification. And that idea, that simple idea of somebody riding in a swing, like a small child, that is the basis of this technology. Okay, so simple ideas lead to very interesting and important physics, and that amplification process is used not just for electrical circuits or mechanics, but it's also used in optical lasers. Use this idea to for in our everyday life. We encounter lasers, and so they also embody some of these simple ideas. So mechanical amplification or parametric amplification has been used for a long time. In fact, many years ago, we demonstrated some ideas related to this with 1 atom thick graphene, that you can actually amplify mechanical motion with essentially, imagine a tabla, but the tabla, one drum, the membrane of the tabla is made out of 1 atom thick graphene. So this idea has very strong basis, except that in the avatar of the device that I will talk about, it doesn't look at mechanical motions, but flow of superconducting circuits. So we will make a...
Can you mute? Yeah,
please
sorry,
go ahead, sir.
please.
Sorry for the disturbance.
Yeah. So in this avatar of the device that I will talk about, we will make a superconducting element, which is and that element is called a Josephson device, and I'll explain the essence of it. But it acts like an inductor. So everybody has used capacitor, resistor, or studied and an inductor in basic electronic circuits. So this device that I will talk about, the superconducting circuit, will actually behave like an inductor. Okay, so we make a RLC circuit, but this inductor is a special inductor, and that actually leads to equations, mathematically the equations same as the equations of a mass attached to a spring. It's not essential to understand, but mathematically they're actually the same. But the basic idea is an RLC circuit. So if you've studied RLC circuits, you know of resonance and quality factor. It's exactly the same idea. So if you know RLC circuits, you already know effectively all the things that I will talk about, except that this inductor is a special kind of inductor, which is made using superconducting components. So the nonlinear Josephson parametric amplifier is the same thing as what I explained to you. It has equation of motion similar to a pendulum or a swing, but it has some additional contributions, which is what makes it a nonlinear device. It has these terms which were not there in the pendulum, and this mathematically this is what happens. But I'll tell you physically what happens is that the pendulum behaves if a simple pendulum, if it moves at small oscillation, it behaves like a linear oscillator. But when you move it at large amplitudes, it will have some terms like these, and that's important for the amplification to happen. Again, we go back to the idea of the spring. Once you have this nonlinear oscillator and this basic circuit, you basically make it oscillate. The electrical energy, when you have a RL, let's say LC circuit, it will oscillate between the capacitor and the inductor back and forth. That's sort of what will happen. As long as the losses are small in the circuit, when you amplify, you put energy at a particular frequency, then if you put a signal at another frequency, that additional signal will get amplified. That's how the amplifier works. And it's been used, demonstrated using by a number of different groups that this parametric amplifier works. But one of the drawbacks of this kind of device is that to tune the inductance of this inductor, you use externally applied magnetic field. And that's sometimes not desirable, particularly if you're measuring quantum circuits, because magnetic field is bad for, in general, bad for qubits. Particularly, one magnetic field of one qubit affects the other adversely. So now let's take a step back. I showed you some equations, but it doesn't really matter what the equations are. But what happens is, can I annotate or? Okay, doesn't matter. So if you have a very nice harmonic oscillator, it is symmetric and it is like a parabola. But the amplifier requires a potential in which the particle sort of moves to have an unharmonicity. And when it moves at large amplitudes, the response, the amplitude, how much it deviates from equilibrium, if I just push the blue ball, it will move, but it moves asymmetrically. And the more it moves, its motion, frequency as a amplitude as a function of frequency is actually very strange and unusual. It looks like this red curve, but before it goes from this nice looking blue curve, which is symmetric, it makes a transition at this point, which is yellow colored curve. At this point, this sort of line or response is nearly vertical, and that is sort of what makes this amplifier work. If you bias the device at this point and you put some electrical signal, then that electrical signal sort of bounces off this biasing point, and you get a large electrical signal because this is very, very steep. Whereas if I send here, then if I send the electrical signal, the output signal bouncing off this line is going to be small. Whereas here, it actually comes out very large. And that's the central idea of this amplifier. And so to make this inductor, special kind of inductor, we take two superconductors and sandwich graphene in between. I'll show you image of that. And many people have studied this. And what it basically ends up doing is that it makes the graphene act as if it's superconducting, even though it's not really superconducting on its own. Okay. And so this inductor is the key part of our amplifier. And the property of this inductor can be tuned by a gate electrode. So I told you that you can make a gate in the earlier field effect transistor geometry. So if you make a gate, you can put more electrons or less electrons here, and that tunes this inductance of this junction, which is a Josephson junction. And that will, as you will see later, tune the resonant frequency of the LC circuit. So let me skip this. Why? So this is the harmonic LC oscillator. Unharmonic LC oscillator is what we actually want. If you just have a completely harmonic oscillator, this amplifier won't work. Now, this LC oscillator can have a frequency which is tunable. So this red line is an experimental measurement, which is the resonant frequency of the circuit tuned with a third knob, electrical knob, which is the gate voltage. This is somebody else's experiment, but I wanted to tell you briefly that other people have used this LC oscillator. Not just that, but they have actually also demonstrated a qubit using graphene. It's actually not a great qubit, but it's because of some loss mechanism inside the graphene Josephson junction. And they have also made some sensors of heat or light. So graphene has this interesting property that its specific heat is very low, so it is used for bolometers quite a bit. And this sort of motivated us to make these devices. So let me just quickly tell you how we make this device. So we peel a graphene, we take a layer of boron nitride, then we take another layer of graphene and then sandwich it between another layer of boron nitride. So we kind of make a sandwich. So imagine taking bread, putting some jam or something in between and another layer of bread. So the bread is the insulator, which doesn't conduct. And the black part is the sort of jam, which is graphene, which is actually going to be the central participant in this device. And so just to show you what this looks like after sandwiching, which requires a lot of skill, which I don't have, but my students are very good. They are much, they're experts at this. They make these kind of devices. So you see layers which are drawn, and then there's graphene in between. And then you make a device by some process similar to what I showed you in a cartoon. We make superconducting contacts, and there is a gate electrode underneath. Now, a supercurrent flows through the graphene just because it is contacted by superconductor. Okay, so this is what the electrical circuit looks like when you want to send electrical signals at high frequencies. So when I say high frequencies, what does high frequency mean? Already in your life, you have used these electrical signals, which is your mobile phones communicate with the tower at the frequencies at which our amplifier works. This is about around 4 or 5 gigahertz, and typical cell phones will also work in the vicinity of that, few gigahertz. Okay, so to carry the electrical signal to this amplifier, you cannot just shine, but you have to guide the electrical signals in. So this is what it looks like. This is 100 micrometers. So this is about a few, something like, let's say 10 hair diameters. So if you pluck your hair and you put 10 of those, then this is will cover this circuit. And this heart of the device looks like this, and its width is about roughly about 1 human hair diameter. So from here to here is 1 human hair. And this is the part where you have graphene in between, and these 2 fingers are the superconductors. So this is the inductor, this is the capacitor. They are in parallel, and that makes the resonator work. This is sort of the effective equivalent circuit of this amplifier, L and C. And so these amplifiers work because they have to work next to qubits. They also work at very low temperatures. So what is low temperature? We cool them down to about 20 millikelvin. So qubits also work around the same temperature. So the idea is that this amplifier will sit right next to the qubit and amplify the electrical chain and send it. So in this case, we demonstrated that by cooling this amplifier down to 20 millikelvin, which is very close to absolute zero. And then you have some well understood, but for a common person, hard to understand, some RF electrical circuit, which brings the electrical signal of 4 gigahertz or 5 gigahertz, sends it to the amplifier, it bounces, gets amplified from the amplifier, comes out, and you can analyze it. If we had the qubit working, the qubit would be here, amplification, and then goes out. Okay. This is fairly standard in RF circuits, whether you use a parametric amplifier or not. The components are well known, except for the parametric amplifier that I'm talking about. So this device works as a superconductor. I can see that because if I measure the current through the device as a function of the gate voltage, and I measure the resistance, then in the region, this sheet of graphene acts like a superconductor, and after some current, it stops being a superconductor and it starts behaving like a normal metal. But in this region is the fun region where we want the amplifier to work. So we will never reach this part. And so when we make an LC resonator circuits out of this same inductor, then as I tune the gate voltage, I change the maximum current which I can drive through this device while it's still superconducting increases. And that is also reflected in the fact that as I tune the gate voltage, the resonant frequency of this LC circuit will have a resonance. This is exactly what's happening here. Resonance frequency changes as I tune the gate voltage. So it tunes from 2 gigahertz to something like 5 gigahertz. Okay, so that the fact that the center frequency can be tuned with the gate voltage is a desirable part of our circuit, and it's done only by applying a voltage. So now comes the fun part. So when you have a resonance at a particular frequency, so when the transition from red to gray happens, this is the resonance, the white region. Now what we do is to make the oscillator, to make this LC oscillator nonlinear, we put a pump signal, which is not the signal that we want to amplify, but another electrical signal that actually shifts the resonance frequency down. Okay, so it moves down. And this is what a nonlinear circuit makes. If it's a completely linear oscillator, then its frequency will not change as a function of power. So the fact that it moves is a kind of first indication that this works as we want it to work. So what we do is we put lots of pump power and we bias it here. And now it's ready to work as an amplifier. This is called the biasing point. And at this point, we send another electrical signal that we will whose amplitude we will measure after it bounces off this amplifier, and that increases its amplitude. There's a gain of something like 24 or 23 dB, which is quite a bit of gain. And then as you go away from the center frequency, it will reduce. So this is sort of a typical amplifier. It doesn't amplify all the frequencies in one go. It amplifies the center frequency more, and then the gain drops, which is kind of there are ways to increase this region of amplification. But what is more exciting about this device is that if I measure the noise, which is undesirable signal added to the amplified electrical signal, that is quite small, and it's actually close to the quantum limit. It's a limit allowed by quantum mechanics, which is set by the temperature at which this amplifier works. It's related to the resonant frequency of this LC oscillator, and that's indicated by the green dashed line. So this amplifier works right at the quantum limit, and that makes it a desirable. So I told you earlier, we want least amount of noise added, and this amplifier does that. And so we studied a number of different aspects of this amplifier. What I'm going to do is skip this, go a little bit fast, and then take some questions. But whenever one makes an amplifier, one has to benchmark several parameters of the circuit. One parameter is called the 1 dB compression point, which tells you how much the gain reduces by 1 dB. How much is that power? So we have characterized that and try to understand how this amplifier works at different frequencies by just tuning the gate voltage. It turns out it's a pretty decent, pretty good amplifier, comparable to the best amplifier, parametric amplifier that's out there in the world, made by other technology, but this is made using graphene. So its performance characteristics are as good as any parametric amplifier. But it has this additional nice desirability, which is tuning happens by a voltage. So I change the voltage, I can get to a different center frequency and amplify signal there. That's essentially sort of the key part. So what I'm going to do is in the next slide summarize what we have shown, that you can actually make an amplifier for amplifying signals from quantum devices using graphene, not just graphene, but a kind of a special superconducting circuit using graphene. And it works very well. And the basic operating principle of this amplifier is similar to the amplifier that you might imagine based on how a child amplifies or increases the motion while changing the standing position in a swing. Okay. One can make lots of different things with it, and our efforts are to make different kind of building blocks or components of quantum devices. That's all I wanted to tell you, and I'm happy to take any questions should you have any. Thank you very much for your patience.
Thank you very much, Mandar, for a nice talk, and I is open for questions. If you have any, if someone has any questions or comment, you can unmute and directly ask, or you can write in the chat box. So Mandar, while they're asking, let me ask you one. So to make it nonlinear, you said you applied one more signal.
Pump,
One more.
yeah.
So that is like, that is also through waveguide. I mean, where is that part in the circuit, the real device?
So
Or
the
it's just
pump,
yeah.
so the pump signal comes through the same path. You can add the pump signal is a kind of a biasing of the transistor of the amplifier, and you can send in the electrical signal. In this demonstration, you send it through the same path, the signal that you want to amplify. Otherwise, for qubits, you can have a separate line to pump. It's called the pump tone, which makes the resonator nonlinear.
I see.
It does, that naturally doesn't come from the device. In fact, it's never at the device. So you don't want to pump at the device at the frequency at which you want to amplify the signal, because then that's pointless. There are some other schemes of parametric amplification, but typically the pump is away from it so that you can distinguish it nicely.
Yeah. Right. So this pump, so I'm trying to see physical. So this pump basically changes the kinetic in the, I mean, why it is making
okay, so
how
let
do
me
yeah.
Let me go back. Let me go back.
Yeah, yeah.
Maybe let's go back to, okay. This is probably the best way to, so see the system is like this, a unharmonic. Nonlinear means unharmonic.
Sure.
And so when you drive it to large amplitudes, so when you put the pump tone, so if the pump tone is small amplitude, it's basically sampling only the lowest part of the potential. So it's sort of like linear. Okay, it doesn't sample the nonlinearity of the system. When you put the pump, it starts sloshing around to large amplitude, and that is where the magic begins. Okay, it pumps it. And another sort of more mathematical way to look at it is that if you have a Lorentzian, the amplitude as a function of frequency is independent of the amplitude of the signal. So it doesn't, you have a resonant frequency. But for a nonlinear thing, when you drive the system hard, it doesn't remain Lorentzian, but it actually starts to have, in fact, multi-valued response. So before that, this part is the interesting point. And so the pump tone brings it to this biasing point, so that it samples a particular magnitude of the nonlinearity.
So in the linear, the gain is 1, right? In the linear circuit, the gain is 1. You don't have any gain.
Linear circuit, you can get a small gain. You mean right here?
No, like LC circuit. Yeah, exactly.
Yeah,
LC
there is no gain.
No gain. It's just, yeah, whatever input, that's the output. So exactly at that kind of picture, when you're vertical, almost vertical, you are, yeah, that's true. So that is the place it is now amplifying the signal. Yeah.
Yeah. Yeah, so there's a question. Maybe I'll come back to your, if you have more questions. There's somebody asking a question. Is the Josephson junction a DC or AC? So thanks for the, so the Josephson junction can be studied using DC electrical signal or AC electrical signal, but it behaves in a kind of a unified manner. So I showed you measurements which are both AC Josephson effect and DC. Because they are the same thing. So this is what you call the DC Josephson, which I just send a DC current and I measure when this Josephson junction starts behaving like a normal resistor, when the superconductivity that is induced in graphene is no longer here, is this light blue region. So this is essentially DC Josephson effect, because that's still sort of governed by the DC Josephson equation. This is AC Josephson effect, if you like, in action. You're exciting a resonance of a LC oscillator, not just the Josephson junction, but a Josephson junction parallel with a capacitor. So that's, I hope that answers your question.
Thank you, sir. Thank you.
Mandar, while, okay, maybe, yeah, before close, no, there is a, okay, no, comment.
Well,
Thank you, sir. Okay, there is, yeah. So Mandar, there is a, this Josephson device, that the diffusive or ballistic, does it have a role in your, this parametric amplifier?
And you mean the transport, whether it's diffusive or ballistic? In principle, it doesn't. It doesn't matter. So the fact that graphene is, whether it's ballistic or not, doesn't make a huge difference. Let me, since you're asking some technical question, the current phase relationship will be somewhat different. It turns out ours is close to the ballistic limit, or at the ballistic limit. But even if it is not ballistic, as long as it's a Josephson junction, there will be some current phase relationship. That may be more complex, but what is more important is that you want some nonlinearities. And the fact that you, in this case, you have some other terms makes it work. So the fact that it's ballistic or diffusive doesn't really make a much difference. In fact, the canonical Josephson junctions that the superconducting qubit community uses, it's the tunneling based superconductor separated by an insulator, and there you just have nothing in the denominator. I as a function of phi is proportional to sine phi. That itself is to begin with a nonlinear system. So the nature of the nonlinearity could change, but specifically the ballistic transport of graphene doesn't play a role.
Okay, I think there are no more questions. Yeah, thanks. Okay, no, okay, there is one question. Yeah.
Yeah, please go ahead if you have a question.
Yeah, no, somebody, you would like to go through the chat, Mandar?
Sure, let me see, where is it? Okay, great. Thanks for this question. This is also a good question. So, so in this case, graphene itself is not a superconductor. So let me give a everyday analogy. Sometimes, you know, in a school, there's a kid who sits in between, who's not so interested in mathematics to begin with, but it sits between two kids who both neighbors like mathematics. So the kid who's sitting in between the two kids who like mathematics also starts enjoying the joys of mathematics or physics or any subject. So exactly same thing we're doing. Graphene itself is not a superconductor, but we put it in between two superconductors, and it starts behaving like a superconductor. So its superconductivity is determined till the temperature that the original neighbors are superconducting. So on the side. So in our case, they are superconducting till about 10 Kelvin, which is still low temperature, but it's still good enough for making the device, because the qubits are anyway sitting at low temperatures. So the short answer is that this amplifier will work up until maybe few hundred Kelvin, few hundred millikelvin, because the superconductor that we have used is a particular superconductor which stays superconducting till about roughly 10 Kelvin. So this amplifier will not work at room temperature. That is sort of categorically I want to. This is a very particular kind of amplifier. It won't be. It's useless for amplifying signals for cell phones, for example. I told you it works in the similar range, because the amplifiers that are there already work well for cell phones. They don't need to be this particular quantum limit. They don't need to add the least amount of noise. So we don't need to try to get it to work at room temperature. So it's a good question. It works at low temperatures up to maybe, let's say, best case in analysis, maybe up to a Kelvin or so, but not at room temperature for sure.
Thank you, sir. Thank you.
Yeah.
Thank you.
Okay, these are good questions. Yeah.
Excellent. I think, I don't see any questions now. So, yeah, Manda, thanks a lot for a wonderful talk. And in fact, I learned many things, and which is very new, this field to me. And good. Venkatesh, can I request you to close this session?
Yes, sir. Yes, sir. So, good evening to everyone. At the outset, it gives me an immense pleasure to propose vote of thanks for all the participants of today's talks. So, we wish to express our sincere thanks to Professor Mandar M. Deshmukh, Professor at Tata Institute of Fundamental Research, Mumbai, for today's very interesting and excellent talk. Thank you very much, sir. And our special thanks to Professor Anindya Das, convener of Bangalore India Nano Monthly Webinar Series 22-23, and Professor of Department of Physics in Institute of Science for his valuable guidance in planning the Bangalore India Nano Talks. I also thank all the distinguished participants of this program, and we look forward to your continued support and participation in the Bangalore India Nano Monthly Webinar Series 22-23. Thank you, one and all, once again. Thank you, sir. Thank you so much.
For the kind invitation, for having me here. Thank you very much.
Yeah,
Thank you very much, Manda. Thank you. Bye-bye.
Bye.
Bye, everyone. Bye.
Thank you, sir.
Thank you. Bye-bye.
Yeah, bye-bye.